I'm Björn, this is Fabian. We both used to work for SoundCloud when we submitted this talk, but now Fabian has upgraded to CoreOS, which makes this talk, I guess, even more meaningful. We collected all the buzzwords, monitoring a Kubernetes-backed microservice architecture with Prometheus. So I'm glad we have a lot of people here. So I guess every single one of you knows Kubernetes and knows about microservice architecture, and perhaps not quite as many know about Prometheus, but by now, I guess it's a pretty popular project. If you had been here last year at this conference, there was a Prometheus talk already, so you might know this slide. Still, since I'm pretty sure it was not everybody, I'll give you a quick recap. So, rewind to 2012, SoundCloud. You might know that site, puts sounds into the cloud, music streaming service. SoundCloud started like every proper startup with a monolithic Ruby on Rails application, which is great. You get something out there quickly. You can iterate fast, really nice, agile, and everything. But should you actually be successful, and successful doesn't mean you are the next Facebook or Google. It's completely sufficient to be 1% of Facebook or Google. You can declare success, but you are in trouble with your Ruby on Rails app because of scalability. The one thing is scalability in terms of capacity. So Ruby on Rails consumes just hilarious amount of resources per logged-in user. You could solve that, like smart sharding schemes, throw a lot of hardware at the problem, perhaps. But then there's another kind of scalability, which is scalability in terms of complexity, and that really kills you. You use Ruby on Rails to iterate fast and launch features quickly, but then the more complex it becomes, this monolith, the more complicated is a feature launch. And at SoundCloud, only like the super old hand people would dare to touch the monolith. And at some point, even they were like, oh, and nobody was launching features anymore. So something had to happen, and some smart people dropped the microservice bomb, right? And as we all know, you just go microservices and all your problems magically disappear. Not quite. So running microservices the right way is hard, and migrating to microservice while you're fully operational is hard. A lot has been talked about that. You can find it on the internet. This is not a talk about how to go microservices and what kind of problems you solve and what kind of new and more interesting problems you will create. But we will talk about two operational aspects of that. And the first is, how do you even run that? Now, you might come up with like buzzwords, Docker, orchestration, cloud platform, whatever. So there are two caveats. First of all, you might not want a cloud platform because you run on bare metal, or at least you might not want a vendor login. So SoundCloud runs a lot of stuff on bare metal, on-premise, and for reasons, like not because we couldn't do it in any other way, but because we want to. And second, it's 2012. 2012 is long ago in a way, right? There was no Docker in 2012. There were containers. Containers were around for quite some time, and SoundCloud was actually running containers in 2012. But you need orchestration for containers, and at that time, even like orchestration systems were kind of difficult. So we created back then our own container orchestration system. Platform as a service, we called it Bazooka. Was supposed to become open source, never happened for reasons. That's essentially in-house Heroku. So it's a platform that runs 12-factor apps. And 12-factor apps, if you don't know about that, look it up. The 12-factor manifesto at 12factor.net, a pretty nice read. It's essentially stateless applications, and that's a good match for microservices. Not for all of them, but for many. So we could run our microservices on that platform. It had restrictions. The obvious one is by design. It would only run 12-factor apps, so you couldn't run your MySQL server on that platform because it needs state. But there were other restrictions that were more like, let's say, design flaws or just implementation flaws. For example, we had very limited resource isolation there, which you could solve with containers, but we didn't. No sidecars. If you don't know what sidecars are, you will learn it later during the talk. And there was like general maturity issues, like first system. it's like this hotel. It's pretty new and everything fails, right? So similar things happen with Bazooka. Sometimes it blows up and we had to do something. So naturally, we would just iterate and improve or rewrite. But meanwhile, the open source world has evolved, and there are a lot of orchestration systems out there. And we did a huge feature comparison, what's good for SoundCloud. And at some point, we made a decision, and the decision was Kubernetes. Fabian will tell you about that.
Yeah, so we settled for Kubernetes in the end. And this talk is not about Kubernetes, so I hope everybody is reasonably familiar with it. There have been 3 talks so far at this conference, all in German though. So we'll try to explain the base concept along as we go. But the basic idea is that Kubernetes was initiated by Google, and so it's built on many, many years of experience from Google on cluster management with containers. And it's not surprising that Kubernetes is very much inspired by concepts from Borg, but is also different in many other ways, which we will see later is a parallelism to Prometheus. There's basically one concept in Kubernetes that does not get as much attention as it probably should.
Full capacity.
And that's labels. So labels are just key value string pairs, and you can basically slap them on everything you have in Kubernetes. You can attach them to your nodes, you can attach them to your services and to your pods, and you can also then select and filter all these entities along these label dimensions. And that's really powerful because you as an operator can basically describe all your entities in an arbitrary way. But the most powerful thing actually is that Kubernetes defines relationships via these labels. So let's imagine you start a pod, which is like this co-scheduled unit of containers, and you want this pod to implement a contract one service provides. And now you don't just deploy this pod and say, okay, you belong to this service. You just throw it out there and tell your service, okay, all the pods with these certain labels attached belong to you, and you can route traffic to these. So it's really like this loose coupling, and it's really flexible. For example, one pod can belong to multiple services at once. And this is what makes Kubernetes probably really powerful. And essentially, labels are the new hierarchies. And as we will see later, labels are the integration point and super important with when we start to monitor this whole thing. But that's basically all there is about Kubernetes from us. And Björn will now go into monitoring at SoundCloud.
Yeah, so because I promised 2 operational aspects, we know now how to run the microservices. Now we have to deal with monitoring them. 2012, rewind again to 2012. That's the year of #monitoring sucks, right? So everybody runs Nagios. We did that too. We're still running Nagios somewhere in the corner. That's a host-based black box monitoring system, right? When it was invented, there was no idea about microservices and stuff like that. So service-based monitoring is really hard. At that time, there was a new kid on the block, which is StatsD. And StatsD helped us to solve some of our problems, not all of them. You can see it here. And StatsD services send UDP packets, one per event, modulo downsampling, to a StatsD server, and that StatsD server aggregates those events, and you can feed it into Graphite. Sounds like a good idea, has a few problems. Let's look at challenges of monitoring microservices. I hate bullet points on slides, but this is just too important. So first of all, why are you going microservices? You have to manage complexity, but you also have to manage capacity, right? You have a lot of traffic to monitor. And you're growing because you're a successful startup. You might be 1% of Google, or next year, 2% of Google. So any monitoring system that has a proportional monitoring traffic, or where your monitoring traffic is proportional to your user traffic, has an inherent problem. Especially if you're over capacity, you now really want your monitoring system to work, right, to handle that situation. But then if your monitoring traffic takes more and more of your network capacity problem, right? Okay, it's not only more traffic to monitor, it's also more targets to monitor. So you're growing, you have more hosts, but then any of these hosts runs multiple containers. And microservices are called micro because they are small, and hosts grow, right? Like 64 cores, something, I don't know how much memory. So you can run a lot of those small containers on a host, and you have a lot of hosts. So way more targets to monitor. That's not everything. Those targets constantly change. In the old world, you had your host that runs Apache. If you update it, you install the new software, restart Apache, little downtime, done, right? Nothing has changed in your setup. In the new world, a deploy is, yeah, let's just scale up a few instances, send a bit canary traffic to it, scale up more, scale down the old version, all those things, right? It's like second nature to us by now. But this is changing where your service instances run. You can scale up for more capacity. You can scale down if you have enough capacity. You can reschedule unhealthy instances, all those things. It's completely dynamic. Why is that a problem? For the monitoring system, it's a problem if you want to fulfill the next 2 points, because you want both. You want a fleet-wide view, overall 99% latency per service or something, which with Studsky is pretty good. But you also want to be able to drill down. Like if your 99% latency is not good, is it a single instance that's upset? Is like a single endpoint not implemented right? Is there a new version and the canary version is slower? Whatever, right? So for investigation, you really want a detailed view. And you want anything in between, right? You want to slice and dice. So both of that together is really hard to get in a monitoring system. But all of that is just means to an end, and the end is meaningful alerting. And that's also a very new thing in the old world. If my Apache server doesn't ping and doesn't respond on the HTTP port, whatever, page somebody has to be woken up. Now, in the new world, you are fault tolerant. Like you have 1,000 hosts, one will always be down, and your system can cope with that. If one of your instances falls over, a new one is spin up, or you have enough capacity, no reason to wake somebody up. So you want something that is called symptom-based alerting. So wake somebody up if your user's experience is impacted or about to be impacted, right? That's the right moment to wake up a human being to come to rescue. Of course, you still want like warning alerts that tell you something is wrong. You can deal with them during your work hours, but you want both. And there's a really nice write-up about that by my former Google colleague, Rob Evershoek, My Philosophy on Alerting. You have a little short link here. This has been around on the internet for quite some time. It's like a holy scripture for me. And your monitoring system should be able to support something like that for pager sanity. Also, you want to monitor everything, all the levels, and ideally not with a different system, or at least with a similar semantics. The network still exists, even if it's kind of software-defined or something. There's still routers and switches. Hosts still exist, even if you're on the cloud. Hardware still fails. Then there are containers, a new addition to the mix, but it has to be monitored. There are applications, as before, they only look different now, and then you have an orchestration system to orchestrate all your containers. Again, something you need to monitor. So in a way, you wanted to get complexity under control with your microservice architecture. In return, you get more complexity, but you got manageable complexity, and you got challenges for your monitoring system. Sneak preview in gray, this is how you get all of those into the Prometheus ecosystem, which spoils the surprise. Prometheus, obviously the solution to all our problems with everything forever, says Benjamin Steffen from Fitbit. So we really like that. We quote it all the time. There's a right with a question mark, which I don't understand because it's obvious, right? So Prometheus is inspired by Google's Bogmon, but it's not Bogmon. It's quite important. Some people blame it's a claim, it's the same. And blamers, it's just a copy. It's actually not. If you have like inside perspective, you won't know that. This is a nice parallelism to Kubernetes and Borg. It's in a way first system, second system with all the advantages of lessons learned. Prometheus was created essentially as an experiment in the living room of Julius Foltz and Matt Proud. They were both former Google engineers. They left the company for reasons, and they suddenly missed their nice infrastructure. And especially back then, we are again in 2012, monitoring was a particular problem. So they created an experiment. Can we have this semantics we know from Google here, somewhere, for like mortal beings? Basically, the fire of the gods. We can bring it to the humans or something, right? So they developed something. It was promising, and they convinced their superiors at SoundCloud to actually invest in that and make it the monitoring system for SoundCloud. It was open source from the beginning. If you knew where to look, you could go to the GitHub org and see all the goodness, but we didn't really make noise about it until we felt it's now ready for prime time, which was in early 2015. So we announced it, and we thought, yeah, like some people, like 5 or 6 will understand what we're doing, and like companies, SoundCloud, Scale, and up might even use that. The response was overwhelming. Like so many people really like that, and somehow we filled the gap, even like for smaller scales, perhaps because it's operationally so simple or something. There was a huge adoption happening. And like yesterday we had Victor's talk where he mentioned all those new things and mentioned in the monitoring chapter, like scenarios have to die, but the replacement presented were actually not quite a fit in my view. And perhaps that on that slide, the gap on that slide, that's perhaps what we filled with Prometheus and what might explain the success. Okay, quick recap for all those who haven't been here last year. What does it do? It collects metrics at scale via HTTP. It pulls them in. This is the first big culture shock here. What? I have to serve HTTP on all my monitor targets? It's actually not a big deal if you're on a microservice architecture because, well, because you serve HTTP anyway in most setups, right? Often microservices talk HTTP to each other. So it's, in a way, yet another client of your microservice, a very lightweight client. And it scales, even if you don't believe that. A single node can monitor thousands of targets, ingest millions of time series at a sample rate of 800,000 samples per second without any external dependencies. There's no distributed storage backend which we use. It's just self-sustained single node, which is important for monitoring system because you need it most dearly if your network is on fire, and then you don't want to depend on your HBase to work or something, right? Some people claim this is not distributed, it can't scale. It's actually not true. It's pretty easy to scale. Would be a different topic, topic of a different talk. Still possible, on and off. Okay, let's go into features. The first thing is multidimensional data model. As long as the projection works. So, a very common metric in the Prometheus world is a counter, and a very common thing to count are HTTP requests. So let's imagine we have a metric, HTTP requests total. That's Prometheus lingo, total for counter. Now, we don't just count all the requests in the company. We count separate by instance, by endpoint, by status code returned, by method used. And so we have a lot of counters, actually quite a lot, because it's the number of metrics times the number of possible values for the instance label times the number of possible values for the path label, and so on. Easily millions, and we don't just save the last value of each counter, we save all those values over time in time series. Millions of time series, that's why we made it scale to millions of time series, because you will have that. You see, parallelism to what we had before. Labels are the new hierarchies. There's a label-based data model, which has many advantages, like in Kubernetes. In Prometheus, the direct advantage is that you can use those labels in a powerful query language called PromptQL, and you can ask questions. And those questions don't have to be baked into your monitoring setup, into your clients, or into the way you collect data. You just collect all those data along all dimensions, and then after the fact, you can ask questions like, what are the 3 path method combinations with the highest number of failing requests? In PromptQL looks like that. You don't have to understand it right now. Or another question, what's the 99th percentile request latency by request path, for example? I mean, let's look at one query in more detail. We can go from the center, like there's our counter, HTTP requests total. It has a status label, and you can select according to that label. This one selects by regular expression all status codes that's 5 something something, right? So all 500 errors are selected. And then take this over the last 5 minutes and calculate a rate. If you calculate a rate over a counter, you get something like queries per second or requests per second. And then sum that up by path and method and show me the top 3 scorers. So you get something like, we are serving 105 queries per second on the API comments endpoint with a method post, for example. This is how it works. You can also graph that nicely and put it into dashboards. Second culture shock, what Prometheus wants you to do is to instrument your code. If you have done StatC, it's not a culture shock at all because it's exactly the same thing. So you want to put instructions into your code to export metrics. It's really easy. We have client libraries in many languages. This is the Python example, which is very straightforward. It's a histogram. We have like counters and histograms and gauges and all those things. Histogram is like a bucketed counter to sample request latencies. The histogram matrix gives you a decorator. You can see that. Down there, request time.time is the decorator. You just decorate a Python function that serves your request, and bang, you get a histogram over request time. And you have to start an HTTP server, which you are probably doing anyway if this is a microservice instance. So this is the way Prometheus wants you to do it. Sometimes you can't instrument your code because it's not your code or you whatever. There might be reasons. And for that, we have so-called integrations. I made this slide like a year ago because I saw that with all the hosted commercial monitoring providers. They have those nice, colorful sheets of logos with all their hundreds of integrations. And I thought, we can do that as well, right? This is old. It should be twice as big by now. Integrations means all kinds of things, like Grafana can plot from a Prometheus data source. That's why Grafana is there. They can feed data into InfluxDB or OpenTSDB. There are also programming languages here because we have client libraries for them. And there is also software that is already instrumented for you with Prometheus metrics, like Kubernetes. You see, there's a connection, or CAdvisor, or etcd. Sometimes, of course, you run a software that is not instrumented, and it will never be instrumented for Prometheus. Let's say MySQL, but there's a MySQL integration. What does that mean? That means MySQL already provides some metrics. There are tables in MySQL. You can query with MySQL, like with SQL instructions, and get metrics out of MySQL. But this is not the way Prometheus understands it. So we created a little separate binary called an exporter that logs into MySQL, queries MySQL, gets all those metrics out, and presents them to Prometheus in a way Prometheus likes it. And that there are hundreds of exporters, hundreds, dozens, and you can use those to get metrics from other third-party products that you can't instrument. Okay, but now talk is half over. Let's come to best friends forever, Kubernetes and Prometheus. Both are kind of Greek, right? It's Greek names, 10 letters, both end on S. The logos are like nicely complementary colors for some reason. So you have seen a few connections already, right? Label-based. Some things play really nicely together. The fun thing is, this is not by design in a way, because Kubernetes and Prometheus were developed completely independent from each other. When we started with Prometheus development, we had no clue that Google has something like Kubernetes in the pipeline. And the Kubernetes engineers, they could have known about Prometheus if they had looked at that GitHub repo, but they didn't. I mean, we know that because they were really pleasantly surprised when they learned about Prometheus in 2015 and started to integrate it. But there's a reason why those systems work so well together. There's kind of a mindset behind it. How do you run large-scale production systems? And this is heavily inspired by how Google runs large-scale production systems. And luckily, they have written all of that into a book. You might have heard about that. I'm totally biased because Niall Murphy was my boss at Google, and I totally like what's written there. I'm biased, but you should read it. It's really good read. Even if you run your system in a different way, there are still many lessons learned, and you get some way how it's done. And those things are easily, you can try all those things at home with all those tools that exist now that are similar to Google infrastructure, among them Kubernetes and Prometheus. It's also fun how, like, I'm pretty sure when they started to work on that book, whatever, 2 years ago or something, you need a few years to get a book out there. They were probably like, yeah, we can tell people how we're doing it, and that you should use Greek name for your projects or something. But people can't try that out at home, right? But now you can, or you could try a few things. But there's an increasing amount of things you can try, and that has a hashtag. I learned that from Fabian at Chorus. It's called Giphy or Jiffy, I don't know. Google infrastructure for everybody else. So that's a great thing. Try that at home, learn lessons, fun. And then, big news last month, Cloud Native Computing Foundation. That's a sub-foundation of the Linux Foundation to support cloud native computing. And they are doing many things, but they also host open source software projects. And the first one they hosted was Kubernetes. And now guess what? What is the second project they're hosting? It's Prometheus. So, natural connection, dream team. They both are living in the same house now. They've moved in. And coming back down to more concrete stuff, 3 questions, how to integrate one with the other. The one is, obviously, you want to monitor your service that runs on Kubernetes with Prometheus. Second thing, remember that table. You want to monitor Kubernetes itself and the containers with Prometheus. And then you want to complete the circle, and you want to run Prometheus itself on Kubernetes. And all of that will be answered by Fabian now.
Yeah. So how do we connect all these things together? So let's imagine we have our Kubernetes cluster running, and we have our namespace, production, development, whatever, and we have a bunch of services in there. And we have pods in these services, or belonging to these services in a way. And you can actually, in this case, label these pods. So we can label a pod with the current software version it's running. So that's really interesting, right? So we can actually distinguish then and select only pods running version X and only pods running version Y. So how do we get all this into Prometheus? Because it's actually also interesting for monitoring. So what you want to do in the end is you want to compare how does version X of the application behave against version Y. Does this recent release fix this latency bug? Or did we actually cause a regression causing this endpoint to error all the time? Or is my canary or development or production namespace behaving differently? So what Prometheus does is we talk directly to the Kubernetes API. You can configure that. And by doing that, we can actually fetch the whole set of pods and constantly listen for updates. So as updates come in to your scheduling in Kubernetes, you will immediately get that into Prometheus, and Prometheus will immediately start and stop monitoring your new pods, or stop monitoring leaving pods. And as we're talking directly to the API, we also have access to all this metadata, like namespace, all the labels, annotations as well, actually. So basically, you can write one configuration for your Prometheus server, and it basically will completely adapt to everything that happens in your cluster. If you deploy a new service, it will start monitoring it out of the box. If you change the scheduling of a service, it will pick up on that and monitor the changes. So yeah, you essentially need 20 lines of configuration, and Prometheus will monitor your entire cluster out of the box. But that's not the only thing why the integration is really great. So we have seen before the exporter concept, and it's everywhere, basically, right? Because if you're using open source software heavily, you're using a lot of software that's not instrumented, or you're running probably a ton of legacy software that you won't bother instrumenting anymore. But you can just write these exporters or take them from open source. And a Kubernetes port is essentially exactly what we want here, because it's co-scheduling of certain containers all the time. So if you are deploying MySQL in Kubernetes, we basically want MySQL exporter to run along each instance of our MySQL server. And yeah, we can just specify that in Kubernetes. And for Prometheus, this is actually completely transparent. So Prometheus just sees a pod and sees, okay, this is an endpoint, I can scrape for metrics. And Prometheus doesn't care if it's an exporter serving these metrics data, or if it's natively directly from the application. So essentially, you can completely hide this whole fact from Prometheus, and monitor your natively implemented services as well as the ones running with exporters. Then there's cluster monitoring. So we have a bunch of components in our cluster, right? We have etcd, which is sort of outside of our cluster, but it's arguably the most important part because it's holding the entire state of everything we have. So we probably want to know if something's up with that. And we can just configure Prometheus to scrape etcd, and etcd natively exports a bunch of Prometheus metrics, and you just typically point Prometheus to the DNS records for etcd or directly to the IPs, because the etcd nodes don't change that frequently. Then we have API servers. These don't have too much metrics. They are basically just exporting a bunch of stuff about how long did queries take, how many queries did I get, etc. And you can just ask the Kubernetes API for all the API servers and yeah, start monitoring them. And it's also natively instrumented, so this works out of the box as well. Then there are kubelets. Kubelets are the local agents running on each node belonging to your cluster. And the kubelet actually exports a ton of metrics. So it has its own metrics, of course, but most importantly, it's embedding CAdvisor directly. So the kubelet essentially exposes metrics about all your containers in your entire cluster, which is metrics about memory usage, memory limits, CPU usage, network, all this stuff. And yeah, all this is exported on each kubelet via an HTTP endpoint, and Prometheus can just scrape it. So we just have to ask the API for all the kubelets, and we are good. Pretty simple, actually. So far, if you look at this, Prometheus is sort of like outside of our cluster, standing on its own, doing its thing, and that actually works. So it's if you're running Prometheus outside of the cluster, this makes many things easier. So if you're just like migrating towards Kubernetes, you probably don't want to migrate your entire monitoring setup as well at the same time. So in this case, you can just keep Prometheus out of your cluster and just monitor the inside from the outside. There are a few things you have to take care of. So your pod IPs, which Prometheus gets from the API server, must be routable from your Prometheus server. And if you've tried that, that can be kind of tricky, but there's a good chance you want to set this up anyway, to basically like make the entire workflow with Kubernetes easier for your developers. But yeah, that's probably the most important point. And yeah, you would just like deploy Prometheus via conventional ways, Chef, Puppet, Ansible, whatever. And you sort of have to configure Prometheus to authenticate against the API server, because if you're not running inside of the cluster, you are not trusted by default. But if you want to run inside of the cluster, you essentially just run kubectl, provide the image path, and you suddenly have a Prometheus server running inside of your cluster. That's sort of a simplification, of course. You want to like expose a port so you can actually access the web UI, and you probably want to basically deploy a config map into Kubernetes so that a configuration is mounted into the Prometheus pod. But aside from that, this is pretty much it. And with that, basically our image doesn't change that much, only that now Prometheus is running inside of the cluster. But essentially it's behaving the same, it's configured the same. It's pretty straightforward. So as Bjorn told you, Prometheus is using local storage. And if you have tried storage in Kubernetes, you probably have run into some questions. It's not that easy. If you're running in AWS or Google Cloud, it's easier. You have cloud volumes, right? But what are the general options? So option A, don't do anything. So you can just use the default temporary file system you get with the pod. And as soon as the pod dies, gets restarted, rescheduled, it's gone. So you lose all your data. But actually, that's not that bad. So if you think about monitoring data, it becomes exponentially less important the older it gets. So I care a lot about the last 5 minutes, right? Because that's necessary for my most critical alerting. Like, is the service available at all? Or is the latency really bad? Then there may be like the last 1 or 2 hours, which is like super good for dashboarding. And yeah, there is use for historic data, but you can get a lot of value out of Prometheus with only having like the last 24 hours. So actually not having persistent storage is a viable option. Yeah, option B is network and cloud volumes. Cloud volumes work great. I mean, it's provided by Google and Amazon. You don't have to care about anything. You just configure Kubernetes to basically mount them into your pod, and you're good. Similar with network storage, like your own on-premise one. So if you have Ceph running and it all works, that's great for you. NFS, for example, does not work because NFS is lacking important features to actually run a database. So probably the most viable option is, if you're small, are host volumes. So you can actually configure Kubernetes to mount a volume directly from the node hosting your pod into the pod, and you can write directly to the node disk. And this will actually persist as your pod dies. And then you can configure Kubernetes to always schedule a certain pod on certain nodes, so they will always be rescheduled, if you do an update, for example, on the same node and mount the same host volume and have the data back. So these are sort of the 3 options. You sort of have to pick a poison. In the long run, we want to have, of course, a long-term remote storage. But as you've seen, we're talking about hundreds of thousands of samples per second from a single Prometheus server. As you grow, you will have more Prometheus servers, and you will probably go towards, I don't know, a few million samples per second. And you sort of need a database that can actually support that for years and years and years. And so far, we haven't found it. So we might want to write our own. We will see. But until then, ABC are the options, I guess. Yeah, and now it's time for demo. Can you read that? No? Cool. So we have sort of a 5 VM Kubernetes cluster running here on my laptop. So we have 4 nodes in the cluster. One is etcd, it's outside of the cluster. And let's see what we have running here. So we have this cluster set up with one Prometheus server and actually an example application that's receiving fake traffic, and it's just sort of emulating a typical microservice or something. And we have a developer namespace where we have 2 instances running of that, and we have a production namespace running 4 of these. And then we have a bunch of stuff of Kubernetes where it's basically self-hosting some components. And if you look at that in Prometheus, we actually see that Prometheus is monitoring a bunch of stuff already. So this is a status page showing you what are our current monitoring targets and what's the status. And we are monitoring our one etcd node. We are monitoring our one Kubernetes API server. And we are monitoring all the 4 kubelets here. And to roughly see how this looks like, that's sort of the metrics page Prometheus sees if it scrapes an endpoint. And each line is basically one metric with the most recent sample value. And if we scroll through that, we see that's like a lot of different metrics. And that's just one single kubelet. And considering you have probably like 100 nodes in your Kubernetes cluster or something, you see how we get all these different metrics. And then we have the example application configured as well. So Prometheus is scraping this example application. And we haven't labeled it because demo. But we have deployed it in different namespaces. And here we actually see that Prometheus took the namespace from Kubernetes and attached it to each target, which essentially means now each metric we scrape from this target will get this namespace equals production or development label attached to each time series. So then we have this dimension available in all our subsequent queries. And we can actually try it out. So I promised you that we are able to really adapt quickly to changes in our cluster. And if we now try to scale this app, let's say in our production namespace, and currently we have 4 running, right? So let's say we want to go to 7. And here we see a bunch of pods, they are still creating. And if you go back to Prometheus, we will see as soon as they are running and available, they show up. And suddenly we are monitoring not 4, but 7 pods of our example application. So all automatic magic. And sort of to see why these dimensions are so important and why we're actually preserving all these dimensions and having them in the first place, let's look at one metric we have from our sample application. So we have this CodeLab API request duration seconds bucket. And that's actually a metric belonging to our histograms. And if we graph that, we will see that it's almost killing our browser. Because this is just like a lot of different time series. It's a lot of information. But the key is it's all necessary. But we can't use it like that, right? We have to basically now define a query that gives us this information in a digestible way. So you don't have to like understand all of this, but let's say we want to now get from this histogram metric, we want to get the 99th percentile of our recurse latency in our demo application. So we have a function, for example, called histogram quantile, and we can actually now calculate any quantile we want, or percentile we want. And we just have to basically do some aggregation now, because we don't want to preserve all these dimensions, right? We don't want to look at every individual pod times every individual method, times every individual namespace, times every individual pass, times every individual status, because it's just too much. So we want to throw out some of these dimensions, sort of aggregate them away. So let's say we want to get rid of the instance, because we want to sort of have a global view on our infrastructure and not just every single instance. And that should work. Yeah, so this is already easier, right? Still apparently a bit too much, because yeah, it's just too many different lines. But we can also get rid of, we can now decide that basically at query time which other dimension we want to aggregate away. So let's say we don't care about the status too much. And now it's even less. So now we can actually, it's a bit easier to digest, right? So now we can like hover over it, and we can see, okay, here we have an example application, and this is the latency for our pass API/bar in our development namespace with the recurse method post. And this now allows us actually to compare between our namespaces, for example, or if we have had labeled all these pods by the software version they were running, we could now distinguish between latencies across versions. And if you're troubleshooting, this is extremely important, because you don't know if a certain pass is flaky, or if it's just a certain like recurse method that's erroring all the time, and you sort of at query time have to ask the right questions. And so we need all these available and be able to query it at read time. So that was basically like this short demo on how it integrates well. I hope it was understandable. And with that, our talk is basically over.
Perfect timing.
Final slide, of course.
Okay, now network. Oh.
We are hiring here in Berlin as well, but also in New York and San Francisco, and we are also hiring Prometheus engineers. So if you want to work on Prometheus, just come to me afterwards, and we can talk. And yeah, PromptQL. It's sold out, so it doesn't help you much, but
we're just teasing you.
We have a Prometheus conference. We should have made it bigger, but we will have high quality videos, and we will upload them for everyone available. So it should still be good, even if you can't attend.
All right. So we have like 50 minutes for questions. And it's so dark that I can't see anybody. But yeah, make yourself. Okay, last row. Yeah, that's for Fabian. What about alerting is the question.
Oh, alerting. Yeah, so how we do alerting basically is, imagine you have all this time series data. And you have this powerful query language, right? So it's like, it's super awesome. And why not just use it for alerting as well? So you can actually like take your query language or your query expression, define an alerting rule. So basically define like for how long it should be firing, or it should yield a result. And then we have the alert manager component, and we sort of Prometheus just evaluates these expressions all the time and determines if it's firing, and then just sends thousands of alerts out to alert manager, and the alert manager then cares about basically aggregating all these dimensions away and basically serving you with a low amount of notifications. So let's say you have an expression about latency, and you can actually filter that out. We can basically do in PromptQL greater than 200. And then basically everything, like every pod that's having a latency over 200 will be one alert. And this can be like hundreds or thousands, right? So we send them out to alert manager, and alert manager then has basically the logic and the sanity to determine what should be aggregated into one notification, so that you get like one notification only, so you don't are spammed, but you basically have this full insight into like every individual thing that's actually causing a problem.
It's also the labels translate through the full stack, right? In the end, you can say, if I have a namespace development label on my alert, I don't want to get paged because it's just development. Or like if it's in the availability zone US East, then I know today I've trained it because it's in maintenance, I can just silence for one day all those alerts from there. It's all consistent, full stack consistency. Okay, more questions. By the way, we are können auch Hochdeutsch, so if you are like scared to ask in English, you can ask us in German. We'll translate. Okay, please. Okay, housekeeping function. So we have a retention time. You can configure that. So you can, by default, it will keep your data for 15 days, and then the rest is deleted. Of course, problematic. If you collect a lot of data, your disk might not even be able to keep 15 days. Then you have to play with it. In the bright future, there might be something like, I have 500 gigabytes of disk space. Please never delete the data once it's full, right? That's not there yet. So you have to tell the server how much you want to keep. But having said that, we have a highly efficient compression behavior on the server. So people are usually surprised how much they can ingest. And just as a data point, SoundCloud runs I don't know, 50 Prometheus servers in the whole company. And we have a server that monitors all the other Prometheus servers. Meta monitoring is also important. And we keep just a year of data. And it fits all on the disk. So in general, if you deal with your time series responsibly, you can keep a lot on a decently sized disk. Okay, more. It's really difficult to see.
Yeah.
You just showed us that endpoint which provides the matrix data.
Yeah.
And how do you deal with data which are getting really big on that? Because it looks like there's all matrix inside that single endpoint. Is there a way to get a partial metric?
So in general, no, because we don't want to do partial scrapes. You get into sort of consistency problems with that. Basically, if you see the text representation you saw is for the user view. So if you just access the endpoint with your browser, you see that. And it's also transfer gzipped. So a lot of these labels are duplicated, right? A lot of that will get compressed really well. But we also have protocol buffers. So Prometheus will actually try to negotiate whether it can scrape protocol buffers or can scrape text protocol. Text protocol gzipped versus protocol buffers is approximately the same efficiency. Doesn't really matter. But in practice, we have at SoundCloud, I think we had endpoints up to 30 megabytes of data. That gets sort of tricky, yeah, if it's 30 megabyte compressed. But yeah, that's also insane, right? So you should rather, you probably rather want to split across multiple endpoints, logical units of metrics, than slapping it all into one endpoint. For example, the kubelet, it has metrics data about the kubelet itself, and it embeds cAdvisor. So you get the cAdvisor metrics and the kubelet metrics on the same endpoint. That's probably not the best idea in general. Yeah, imagine your microservice instance, right? You maybe have 1,000 metrics. That would be a lot. That's small in general.
Yeah.
Yeah. Yeah. Yep.
Yeah, the JMX exporter. It's also, you have to handle all those metrics responsibly. You can easily blow up your server by just doing something crazy. And the JMX exporter is particularly prone to that because you have so many metrics already at your fingertips. Yeah, let's export everything to Prometheus, and then weird things might happen. The common pitfall is to let the number of time series explode by having too many label values. So the SoundCloud, the proverbial SoundCloud caveat is, yeah, let's put the user ID into a label. And SoundCloud has hundreds of millions of unique users a month, so you get hundreds of millions of time series a month. That doesn't work, right? Millions is the number you shouldn't exceed. So that's your currency you have to deal with. You watch it.
Rule of thumb is, I would say, if you have a label, you should be able to write down all the possible values on paper, like an HTTP method, right? Post, get, head, etc. If it's unbounded, it's probably wrong, except for container IDs or IPs. Yeah?
How often are you polling those endpoints?
Configurable. That's configurable, essentially. You typically...
Out of the box or desktop?
30.
15 seconds, I think it's default,
30.
or 30, whatever. Like, it depends really what you're doing. Like 30 seconds is probably a good rule of thumb. Some people just need like every couple of minutes, but that would be on the long side. We have a MySQL high-frequency Prometheus just for very specific purposes that scrapes every second. A curious fact, on older versions, the syntax of the configuration file wasn't able to specify anything below 1 second, but we changed that. So I've just run load tests with like 500 milliseconds scrape interval, but that's getting crazy, right? It's not like literally a high-frequency monitoring tool like you would use for science with like, I don't know, microsecond scrape intervals or something. Seconds.
Actually, Bacona does the sub-second scraping.
They do sub-second, okay. Yeah. But that's really like, this is niche case, right?
Yeah.
Okay, yes, please.
How can I integrate this in my existing monitoring solution? Like using a tool in my case?
Yeah, many. Do you want to take that, or should I?
Migrate. No, for example, for alerting, we sort of have this plugin that you can actually make Prometheus basically collect data and basically send alerting via Nagios. So that direction works. In general, it's like a very different concept. I think I like that sort of like black box probing, right? And there's no real right path back into Prometheus, for example. So alerting out, good. Back in, it's a problem.
In general, like black box and white box monitoring is something you want to have both, and Prometheus was always meant as a white box monitoring tool. Having said that, there's a Blackbox exporter that essentially does black box probing and exports it to Prometheus. So you could go all in, but like SoundCloud is a really nice case where we still have Nagios around, right? We have this. The alerting was done via Nagios with that plugin, so we had really what's this graceful. Whatever, I'm missing the word. Also, Stutzy is still running somewhere, and then you can combine like graphite data. It can be displayed with Grafana next, even in the same display if you want, with Prometheus data. So there are loads of integration points. It really depends on circumstances, but a smooth transition is possible. Okay, yeah. So I'll answer the database and
yeah, the stuff is the second, it's easier. Essentially, if Prometheus is down, first of all, HA, so run 2 of each, right? And meta monitoring. So imagine you have like your Prometheus servers, you have 2 of them, then you have 2 meta monitoring servers monitoring all these, and these are monitoring each other as well. So you sort of close the circle by having an HA monitoring and meta monitoring pair.
Yeah, and database, essentially, we are having an embedded database, right? It's not that Prometheus doesn't use a database, it has a database. It's just embedded. In the prehistorical version of Prometheus, we were just using LevelDB for everything as an embedded database. But that's not really, like, we saw that at least for the raw sample data, we need a dedicated time series store, and we were really reluctant. Like, we are not storage experts. We were not like, yeah, we can just implement that, right? So we were really exploring all our options, and in the end, we found out, okay, there's nothing out there that pulls it off, so we have to do our own thing. We were really like, oh my God, if a storage expert looks at that, they will all laugh at us or something. But in the end, we found out we are kind of, we're leading the industry essentially with our embedded time series storage. So when we had done our normal implementation, Facebook published the Gorilla in-memory time series database. That was super intriguing because they essentially solved a very similar problem. And there were many similarities, some differences. And then I got inspired to put some lessons from that paper into Prometheus again. And now we are we basically compress to 1.3 bytes per sample. And I think nobody else is doing that. But this is all raw sample data for indices. We still use LevelDB. That might change. Like Fabian is doing some exploration work in that area. There's a talk at PromptQL about that. So it's a really exciting field. The important thing is it's not a general purpose time series database. It's just for our purpose, and it has to be embedded. Like, we didn't want anything external where you need to access the network or have a lot of complexity in like other binaries. Okay, I think we can take one more question, and then you've earned your lunch. Anyone? Ah, there's one.
So it's not partitioned. So the idea is basically your monitoring has to be alive and everything else fails, right? So you can't really rely on your alerting not working because you have some net split or something. So everything your one Prometheus server collects is stored on its local disk. So you can always, in case of emergency, go back to it and query all the data it has. And what you usually do is functional sharding. So let's say you have many services, right? You can easily like monitor 1,000 instances of one service with a single Prometheus server, but you probably like shouldn't monitor like your 1 million containers of your 500 services with one Prometheus server. So you do functional sharding. So you basically allocate certain Prometheus servers to monitor different things. So I monitor my databases with that one, my front-end microservices with that one, and that's how you do like the first layer of sharding. If you grow beyond that, you can actually do sort of partition sharding. And what you do then is you aggregate the data as it comes in, because it's like a lot of data. So you aggregate, for example, the instance label away and federate that back up to a higher up Prometheus server, where you then have basically the view across the whole fleet. But so far, we only know one company who's actually doing this sharding.
Yeah, and then there's Google. They have their own monitoring system, obviously, but if people tell us this doesn't scale, then what's the most scaled system on this globe? It's like Google, and they use exactly the same concept. And it's, as you can see in the SRE book, I really like how they write, like, we don't do magic. We try to solve problems in the most simple possible way, because this is the way that will not fail, right? And they don't do like fancy distributed query evaluation or something. They just do what Fabian just described, right? They have like local monitoring servers, and they aggregate the high-level metrics into global monitoring servers, so they can look at the global thing for like global QBS, and if they see there's a problem in that area, they drill down on that local server and explore other stuff. Okay, but now I think we are really out of time. Yeah. We are still around. Catch us, ask us questions, and enjoy your lunch.